Here's our angle question. The television camera is positioned 4,000 feet from the base of a rocket launching pad. The rocket shoots up into the air. Its speed is 600 feet per second. When it has risen 3,000 feet. How fast is the distance from the television camera to the rocket changing at that moment? And if the television camera is always focused on the rocket, how fast is the angle of elevation changing? So, first of all, I'm going to draw my diagram, and on my diagram, I'm just going to show here little arrows on the y, the z, and the theta. Because we have one diagram where we show variables that are changing, and then we're going to have a second diagram to talk about a specific time. Here's my second diagram. We want to know exactly when it is 3,000 feet. So this makes a nice 3, 4, 5 triangle as a result. The 4,000 was fixed. So what do we know? Y of t is changing, z of t is changing, but x does not change because it's set at 4,000. And part A is actually a triangle question from before. Okay, we know that dy dt is 600 feet per second. We want to find dz dt. Technically, dx dt is equal to 0. And from our second triangle, we know that when y is 3,000, z has to be 5,000. Now, two ways of going about this. We set up our equation. One way you could set up your equation is x squared plus y squared equals z squared. Or you could set this up because the x is set at 4,000, we could write this as 4,000 squared plus y squared equals z squared. I actually probably prefer the second one because when I take the derivative, if I take the derivative of the first one, I would get 2x dx dt plus 2y dy dt equals 2z dz dt. Can you see that if you took the derivative of the second one, and I'll do it in purple here, you just get a 0 with the x. I like that better, getting the 0 right away. Do you know that your dx dt is 0? So that's going to be 0 that way anyways, because x is not changing. But in our diagram where things are changing, if something is fixed, you can use that value in your equation. Now we can just plug in the values that we had from before and solve for dz dt. This question is a review question from before. What we're doing new in this section is thinking about the angle. Because the angle is also changing. Everybody good? Almost? So we still have to do part B of this one. Good? Awesome. So for part B, we've got the same diagram, we've got the same specific situation. Theta of t is changing, y of t is changing. Technically, z of t is still changing as well. But if I can reduce myself to using less variables, that's going to be nicer. And in this situation, is there a way to relate theta and just y? Yes, we can do that with tan. So we want to find d theta dt. We know dy dt is still 600. Technically, we could solve for theta, right? You have SOHCAHTOA. I'd be going back to grade 10 math. You could solve for theta, no problem. I write that technically because we're going to find out, and we can actually skip solving for it if we want to, making our life even easier. But we'll get there in a second. Okay? So if I did the derivative with respect to time, the derivative of tan is secant squared theta, and then it's a chain rule, d theta dt, equals 1 over 4,000 dy dt. Now, secant squared is 1 over cos squared theta. And I could get my d theta dt by itself. I could solve for the angle, or I have 600 over 4,000. This is a 3, 4, 5 triangle. What is cos of theta? Adjacent over hypotenuse. So 4,000 over 5,000, which I could reduce to 4 over 5, because that's cos of theta, and still square it. And then I wouldn't have to find theta. So I could use SOHCAHTOA and find theta, or I could skip that and get my value this way. And either way, if you type this into your calculator, you will get that as an answer. For me, which do I prefer? I kind of prefer not having to use my calculator at all. Until, and even in the end, this is going to give me a nice answer that's going to be a fraction. Otherwise, I would have to do some more stuff with my calculator. Oh, look at this. This is 4,000. Sorry. So could I simplify this even more? Sure, this could be 3. This would be 6 over 40, which is 3 over 20, times 16 over 25. Beautifully. Okay, it's going to come eventually. And then, of course, the 16 and the 20 have a 4 in common, so if I divide them both by 4, that would be 4 and 5, and I get 12 over 125. Which, if you type that in your calculator, you're going to get decimal 0.96 that way as well. Okay, important. I don't know if we've talked about this explicitly, but all of your derivatives of everything we've done so far in trig only make sense in radians. So the question does not have to say units. If you're going to use derivatives, you are automatically in radians. Which would be a question you have in this question. Question you would have in this question. Sort of like, oh, what are my units? It didn't say radians or degrees. The derivative of sine is cosine, only makes sense in radians. But I don't know if we explicitly said that, or maybe we did, and you're like forgotten about it so much because we never talk about it. It comes up important in a question like this. Okay. Another angle question. A kite 100 feet above the ground moves horizontally at a speed of 8 feet per second. At what rate is the angle between the string and the horizontal decreasing when 200 feet of string have been let out. I'm going to tell you that your number one issue with these questions is probably your ability to draw a picture. Okay? So, maybe at the top of your page, try sketching it on your own. And then label the things that are changing with variables. Because drawing the diagram is going to be key to figuring this out. Now, if you don't want to cheat, don't look at the board as I show it. If you've got your diagram, see if yours is closer. Did anybody draw the exact same thing this way? And have your theta there. Okay, it's actually the same triangle. Okay. So that would also be correct. What's changing? X is changing. You are a masterful kite flyer that you keep it constant at 100. You're going to let the string out just perfectly so that it maintains that 100 feet. Okay. Technically, I don't like my diagram a little bit because what else is changing? Okay. I would actually put this in there and then draw the specific. This is the specific. Maybe it'll eventually show up. Oh, here's theta. Oh. Okay, so let's make that box disappear. And there's my sad face. There we go. X of t is changing. Theta of t is changing. Technically, z of t is also changing because you're letting out string. Okay? But can we make an equation just with x and theta? Yes. We can make an equation with tan. These are almost exclusively tan questions. This could be a non-calculator question. Let's check it out. So we take our derivative. Derivative of tan is secant squared, which you could write as 1 over cos squared theta. And do you recognize that 1/2 for sine is your pi over 6 family? We also don't have x, so we can do a squared plus b squared equals c squared. To get our x value in our specific triangle is 100 root 3. Of course, cos of pi over 6 is root 3 over 2, so cos squared will be 3 over 4. And again, our units are radians per second.